Hi, this is Liz Chatelain, and I'm really excited today here at LGDinTECH. We are interviewing the president and founder of Synova. Synova is synonymous with laser systems, and frankly, they're the pinnacle. Everybody wants a Synova, and even people in all sorts of materials use Synova laser systems, but especially in diamond. It's sort of the crown jewel in diamond if you have Synova equipment. They know those either growers or post-growth service providers or end users, they can trust Synova equipment to be as, pinpointed in perfection as possible. So with all that said, we have a series of questions. If you have additional questions after you view this, put it into our feed bank and we'll try to go back to Synova and get answers for you. Hi, I'm Liz Chatelain, the co-founder of LGDinTECH. We're here as a conduit for you to link up with prime growers who are working on technology-grade grown diamond around the world. So if your application has anything to do with, say, heat management, or you need wide band gap, or outstanding electrical transport of any means, diamond can probably be your solution. So reach out to us. Quickly go to our website, lgdintech.org. On our homepage, right under our logo, there's a link there for request samples. Click on that, and then you'll make a quick appointment with Marty Hurwitz, my other co-founder, who will spend a few minutes on the phone with you trying to narrow down exactly what your application is, so then we can introduce you to the perfect companies that can work on your solution with you. Our first question is the cold advantage for quantum sensitivity. Deep tech developers are developing and using diamond quantum applications where even the smallest lattice damage is totally unacceptable. Can you explain to us how the water jet cooling in your Laser MicroJet technology specifically preserves the atomic integrity of the diamond surface compared to traditional dry laser dicing? And do you have data on this cold effectiveness from downstream performance in semiconductor applications?
Yeah, wonderful. Thank you for this question. Indeed, the water jet guided laser combines a water jet to guide the laser beam and the laser itself. And the water jet is not abrasive. The water jet is just there to guide the laser beam and to cool the material, the cutting edges during the laser ablation. The original, motivation to combine these two, let's say, processes, these two technologies, was to avoid any heat damage, heat affection to the material. So it was exactly, the reason for the invention of this technology. And the original, the first application was the medicine. The application was to remove caries from the tooth, and the nerve, below or inside the tooth is very heat sensitive. You can also say somehow there's nothing more heat sensitive than your own body, than the nerves in your body, and it's just a few degrees too hot, and they will die or they will be damaged. So later on we moved into industrial applications, but the effect of cooling is exactly the same in the material. That means with the water jet that is constantly flowing, the laser beam is pulsed. It means between the laser pulses, the water jet removes the heat that has been just deposited by the laser pulse before. And you have to imagine that the repetition rate of our laser is in the range of 10,000 hertz, meaning 10,000 pulses per second. This heating, ablation, and cooling happens with each and every laser pulse. So it can be, 10,000 times per second. So it means the heat cannot penetrate by heat conduction inside the material and create the so-called heat affected zone. And this means, the structural changes, the damages in the material, the micro cracks, the remelt zone, and so on. So all this we can avoid with this combination of low pressure water jet that just cools the material, it does not ablate it, and, the high power laser beam. And now you ask, what exactly happens and how does it, work in the case of semiconductors? So it's very difficult really to measure because it's so fast a process to measure now the temperature in the cutting edge. But we can analyze the result. Now this, all our customers have done. They can, everyone has been able to confirm that, the Laser MicroJet leaves the material intact and the structure does not change it. No, it is in the semiconductor material, whether it's silicon or any other compound semiconductor. It's always the same effect. The heat, let's say, impact is only around maybe 2 or 3 microns, from the edge, and then below there's nothing. There is really no change in the structure of the material or of the semiconductor. So that's the reason why we can say that Laser MicroJet is the safest or the most gentle cutting technology in the world, and especially interesting for semiconductors, for modern or new types of semiconductors, like the quantum computing chips. And I can tell you that we have already sold either machines or sold our service to cut chips for quantum computing. That means our technology is already used in this industry.
That's fantastic. Thank you so much. That's a great answer. And I'm sure people within the supply chain are very interested because they need perfection.
Yes.
This is an application. This is a material within materials. So they need perfection. They can't be the holdup. And speaking of bottlenecks, our next question is about solving the water slicing bottleneck. So our audience scales from growing single stones to producing 2 and 4 inch diamond wafers. Slicing effectiveness becomes primary bottleneck for them. How does Synova technology compare to wire sawing or dry laser splitting in terms of Kelf loss, speed in which processing services, service areas and CVD blocks? And is your equipment ready to handle fab level throughput required for the next generation of electronics?
Yeah, thank you very much. I think that's also a very important question. One technology, let's say the present technology to slice silicon ingots is the wire saw. And it's very, let's say, simple and purely mechanic, this process. But silicon is quite smooth material, quite easy to ablate with a tool that has hard, let's say, materials particles on the wire that allows to cut through these ingots. Now, when you go to diamond, you have the hardest material in the world, and to cut mechanically a hard material, you normally need a harder material. Because you don't want to cut the tool, you want to cut the workpiece. So, but with diamond, you can only take another diamond. So you can cut diamond with another diamond, but very slow. As you know from the grinding, polishing diamond stones for the jewelry, it's just too slow. It means even the best diamond wire saw in the world applied for diamond substrates slicing would be not economic at all. So it would be much too slow. It would take forever. So that we can forget. Then let's take the dry laser. Now, the dry laser today is a very well-used known tool and process. But don't forget now the shape of the dry laser beam. Because of the divergency of the laser beam, the dry laser has the so-called V shape, or X shape, you can also say, because, we have to focus the laser beam, we have a focal point, and below the focal point, the laser continues in a divergent way. And that slicing means you have to cut through quite thick material. We talk about centimeters. And now with this V shape of the laser beam, you very much limited. That means, for example, if today you want to slice or cut a 1 centimeter diamond stone, you lose a lot of material because you have to ablate, line by line, also vertically to the cutting direction, horizontally, I should say, and you have to remove all the material in this steam so that you can go down to the bottom, of this material, of the thickness. So this makes the dry laser more and more inattractive, or less attractive. Less thicker is the material. And now comes into this game the Laser MicroJet that has the big advantage of a parallel laser beam. Straight, very narrow, and it's like a wire. Our water jet is really like a wire. The length today you can maintain is up to 10 centimeter. But honestly, we can today use approximately 50 millimeter of water jet, meaning perfect laminar water jet that guides the laser beam. So we can cut to 50 millimeter of silicon, but also silicon carbide or diamond with our water jet guided laser. And now you can also imagine that if you just cut from both sides, for example, you have a cylindrical workpiece and you rotate it and you keep your laser water jet from the top, we have only to cut the radius. So at the end we can cut twice that depth of 50 millimeter. So we have been able to show that it works in silicon, also silicon carbide, which is another very hard material. Not as hard as diamond, but also very hard, very difficult to slice. And now what I can tell you, we have sold machines to this industry, for slicing of diamonds. But at the moment, our customers are asking us, let's say 35 millimeter, and I want to go into 50 millimeter. It's not yet really a standard in this industry. Let's say 100 millimeter, which is 4 inches. This will take still a bit of time, but it is clearly development. And everyone says the only technology that makes sense, that can be used, to slice our future diamond wafers, is water jet guided laser. There's no doubt. I think that's clear.
So do you think the speed in which the laser can cut can be improved?
Very good point, because it's still quite slow, and now the volume is still low, so our customers accept the speed for the time being. Also because there's no other solution, to slice these thick diamond substrates or metal substrate. It's still the ingot before the wafer shape. Yes, we have to increase still the speed. I think we can do it with more laser power. That's something we are here developing in Synova. We went from 100 watts to 200 watts, then to 400 watts. Green laser powers. Today we apply green lasers. Maybe in the next future, in the next years in the future, we think about blue lasers. But we let's say we follow the development of new laser sources and new wavelengths that even fit better to our water jet laser guide, meaning our thin laser MicroJet, and I think it's a matter of time, that we reach higher speeds and higher throughput.
So our next question is about composite material processing, hybrid composite material. Many of our product developers aren't just using pure diamond. They're integrating it within complex stacks with materials like gallium nitrate and silicon for heat sinks and chips. Since the Laser MicroJet is material agnostic, can you walk us through how it handles the surfaces between these different kinds of materials without causing damage or shattering the weakest layer in the stack?
Yes, with pleasure. So let's say for us, these hard materials represent no problem. Meaning, as harder, always you can say, as harder the material is, as harder and more brittle the material is, as better it is for us. So we can say, all these materials like gallium nitride, silicon carbide, with diamond, of course, it can be layers, it can be even a compound material. For example, we have been recently tested for a compound material that consists of silicon carbide and synthetic diamond. Yeah, it's a homogeneous material. It's a compound material, and they have found out that Laser MicroJet is the best technology to cut it, to slice it, to machine it. Because there's another thing I want to mention in this regard. A big topic in the semiconductor industry is today new substrate materials. So the move from silicon to other, semiconductor materials that have different properties, especially heat conduction properties, conductivity properties. So, because silicon has a limited capacity to conduct heat. Today, the chips are getting so hot that they have troubles to get out the heat of the chip. And ideally, the substrate material is very heat conductive. So customers looking for more heat conductive materials, it can be silicon carbide. For example, for the power chips in the EV industry, for the electrical vehicles, they use a lot of silicon carbide chips. So this is one area. It is power chips. Then gallium nitride is another, let's say, option that is more and more interesting for the semiconductor industry. And then diamond in the form of compound material, as I just mentioned before. Either it can be stacked, as you mentioned, just another layer on top of the silicon transistor layer. Now you can see to remove the heat very efficiently with a water circuit, for example. And then at the end, we talk also about pure diamond substrates and diamond transistors. And so we already cooperate with universities around the world, also in Japan, to apply our technology to dice or slice these diamond transistor chips. And it's today it's possible, to produce, with a long lifetime, diamond transistors on a diamond substrate. And we have been told the success and the future of diamond semiconductors is directly related to your technology, meaning to the Laser MicroJet, because it is absolutely necessary to have this technology for the machining of this extremely hard material.
Very interesting. Very, very true. I can see why they would say that. Hi, I'm Liz Chatelain, the co-founder of LGDinTECH. Don't mean to interrupt the presentation today, but I wanted to just let you know, if you're looking to connect with prime growers and post-growth service providers of technology-grade grown diamond, we can help you. This is really part of our mandate. All you have to do is go to our website, LGDinTech.org. On our homepage, right under our logo, there's a link that says Request Samples. From there, you can book a quick appointment on the phone with my other co-founder, Marty Hurwitz. He's going to ask you questions about your application, so that way we can guide you to the perfect team out there that is working to bring you the best product to make your applications really successful. Okay, our last question today is about the transition that diamond material is going through. So basically from artisan using natural diamond to, technology, automated fabs, everything, into using grown diamond. So technology-grade grown diamond producers are moving towards full automation and clean room-style manufacturing environments, something that the diamond, historically, the diamond industry hasn't been interested in, hasn't needed until they started embracing using the material and technology. So similar to traditional, these clean rooms or whole setup, they're reconfiguring their factories to be more in line with traditional semiconductor fabs. How is Synova adapting all of its laser platforms to support this shift? Specifically, do you see a future where your systems integrate directly inline metrology to address cutting parameters in real-time basis on unique defects into each grown crystal?
Thank you. Yeah, first, maybe let me say that Synova has history in this industry. So Synova was the first company who introduced the word of laser dicing many years ago, roughly 20 years ago, for dicing of silicon wafers into chips. At the time, there was still, the dicing blade was still today is the most, let's say, used technology to cut a wafer or dice a wafer into chips. We thought we can do everything with the laser. It's also true. The other thing is that silicon was an easy material for a dicing saw, mechanical process that everyone knows, to cut through it. So, the should I say, motivation, to change to a laser-based technology that is more complex and more expensive was not really there. Although we have built a few machines for the semiconductor industry, but related or limited to geometry of the cutting line that the dicing saw cannot do. Dicing saws can only do straight cutting lines. But as soon as you need round corners, you need hexagonal chips, or you have different chip sizes on one wafer, there's no possibility to use a dicing blade. So these areas, the laser microJet has been, able to enter. But not in the big volume. So let's say somehow we have to be patient for a long time and to wait that the industry moves from silicon to materials, brittle and hard, that are much more difficult to dice with a dicing saw. No? So, and that's now Synova's, let's say, opportunity today to offer a solution to these new, semiconductor substrate materials. And I always send to, let's say, to my staff here, to our customers as well. We have to wait, on new materials. This MicroJet is the solution for new materials, whether we talk about, ceramics, new, combination of materials, compound materials. That is, the future of the water-jet-guided laser. Not the traditional materials where, established processes do their job quite well. Yes, and I think Synova is able to deliver clean room machines. We have shown this in the past. Yeah, that is not a problem. Then also we work today with partners for the automation, wafer loading, and then also alignment, automatic, alignment of the cut. You just mentioned, also the feedback can be measured, in parallel to our processing. So in this regard, Synova has developed, a number of sensors with our technology to be able to keep, the result, constant and have always the same perfection, when the technology is applied, for example, for dicing of chips. So I think we have today a lot of process control functions that are patented by Synova, and that only Synova can provide now. With our technology, and therefore also we work with OEM partners for example, in Japan, but also soon in China, where our technology is integrated into, a complete automated line, production line, you can say, including, or let's say, in integrating other technologies, like we have developed a machine for cutting a ring from so-called taiko wafers. It's a silicon wafer with very thin substrates, and then very thick border or edge of this wafer to keep the wafer stable, because it's very thin. We talk about a few tenths of microns of thickness, and this ring has to be cut off. And here we have developed a complete machine which is as big as larger than a car. And there's taping, untaping, there are control, there are robots, there are cassettes, there's our cutting station, fully automatic, and we have already built 10 of these machines together with 2 big Japanese semiconductor companies for a very large Japanese semiconductor chip maker. So we can repeat this, and I think we can offer also nowadays customized solutions, real production solutions. Yeah. And so I think Synova can respond to any demand. We start also, to produce part of our machines, in Asia, which becomes more and more important. Although here in Switzerland, we keep our headquarters, and here's the brain, you can say, of our technology. Here's our R&D center, and innovations will come always from here, for sure.
So you see that collaboration and being able to take on the challenge of integrating technology-grade grown diamond into a manufacturing supply line, and into the factory itself.
Absolutely.
Because you're doing that with other materials.
Mm-hmm. Right. Absolutely. And I think we know what we can do and what we cannot do, and therefore, so we work with partners. So we have partners for as I just mentioned, for automation, for other process steps, and the laser MicroJet is just one of the full solution. And but the good thing is, or the good news is, that the laser MicroJet can be integrated in a 24-hour running production line in a fully automatic process. We have shown it in other industries which are very sensitive in regard to quality and constant of results, like the aerospace industry, where we have delivered machines to produce parts for the jet engines. And we talk about the big, engine makers who supply their engines to the big airplane makers, which we all know very well and we use so frequently. And we are very proud to say that all these parts are flying since many years, and these companies have confidence and trust into our technology, into Synova, into the people, into our services. And I think we can absolutely, let's say, repeat the success in the semiconductor industry without any problem.
So let me ask you then, have you in your, outreach and people, different types of companies that come to you, do you see an uptick in the interest from not from diamond producers, but from down the supply, down the pipeline, down the manufacturing supply chain? Are people asking you more about technology diamond?
Yes, you are so right. So now let's say the interest comes not only from the electrode industry, but rather from industries that are much higher in the production line from the basic material to finished electronic products. And we see now is interest and demands coming from large, even imagine software producers or internet solution providers that knock on our door and that ask us, can't we use your technology to cut silicon carbide glasses for virtual reality devices or combine materials between glass and silicon for micro OLEDs and so on. So, and our technology, we are very happy about this, is known. Even this, big, let's say, IT companies, for example, in the United States. And they are very happy that, that there is a new technology available, that, gives a response to the new, let's say, requirements, of the industry with all these new materials for devices. I think that's really great for us.
And so, has anyone actually mentioned diamond in your connection with these different?
Absolutely.
Do you know if they're asking for a particular use? Like we think we can use diamond for X. Is that? Can you provide that maybe, or can who would be providing that? Are those type of conversations happening?
Yes, definitely. So now I think we are well known in the diamond industry, and because of, I think, our great experience and success in the electro diamond industry for now about 16 years. And as you said at the beginning in the introduction, that Laser MicroJet is, let's say the star among the diamond cutting machines, and everyone wants to have one. That's absolutely true. And we learned so much, about the material, the requirements, and cutting towards big diamonds. See, the largest diamonds in the world, natural diamonds, most expensive, have been exclusively cut on a laser MicroJet machine. And we have been told that thanks to our technology, they can save very expensive material because of the parallel cut instead of the V-shaped. The remaining, parts, when, such a big natural diamond is cut, in order to make a jewelry out of it, has such a big, advantage. We have even once that it was like that the profit of the owner of our machine to cut one diamond was higher than the price of our machine. Can you imagine this? So,
wow.
And it's also, all this experience, I think, can be now is important for us. It's very useful to cut, of course, electron diamond, because the chemical structure, as we know, is the same, and we can apply, one-to-one this experience from our 16 years of natural diamond industry into the electron industry. I think that's recognized, I think, almost in the whole world. And so I think we are the top address for cutting of machining of diamonds. And again, just can invite you to ask to put a question into maybe Google or ChatGPT. What is the best technology to cut diamond? And you will immediately be able to read the water-jet guided laser. So I think it's well known in the world.
Very good. Very true. All right. Well, we have really appreciated this time together. Great answers, very educational, and great insight. And we appreciate your time.